Hi, welcome back to my class in Plain Trigonometry. For today, we will take up the fundamental trigonometric identities. And there are 8 fundamental trigonometric identities, and they are grouped into 3 categories or 3 sets. Fundamental trigonometric identities. The first set of trigonometric identities is known as the ratio relations. And there are 2 ratio relations. The second set of fundamental trigonometric identities is known as the reciprocal relations. And there are 3 fundamental trigonometric identities under this second group. And the last group of trigonometric identities is the Pythagorean identities. And there are also 3 fundamental trigonometric identities under this third group. And if you will add 2, 3, and 3, you get a total of 8. Which means that there are 8 fundamental trigonometric identities. Now, the last group is known as the last set of 3 fundamental identities is known as Pythagorean identities because they are derived from the equation using Pythagorean Theorem. Now, we state the first 2 of the 8 trigonometric identities, and they are known as reciprocal relations. The first 2 of the 8 trigonometric identities are known as the ratio relations. The first one is the ratio of sine theta and cosine theta. And the ratio of these 2 trigonometric functions is known as tangent. Tangent of theta. Tangent of theta is equal to the ratio of sine theta and cosine theta. If you take the reciprocal of this ratio, sine over cosine, you get the second ratio relation. And the reciprocal of sine over cosine is cosine over sine. And the ratio of cosine and sine is known as cotangent of theta, which is equal to the reciprocal of tangent. These are the 2 ratio relations. The ratio of sine and cosine, or sine over cosine, is tangent. And cotangent theta is equal to the ratio of cotangent, the ratio of cosine and sine, or cotangent theta equals cosine over sine. I will prove the first ratio relation, and for your assignment, you prove number 2. I will prove the first ratio relation. Consider this right triangle where the acute angle theta is placed at this vertex. And the side opposite the right angle is the hypotenuse whose length is r. And the side opposite the acute angle theta I denoted by x. And the side adjacent to the angle theta I denoted by y. And we want to prove We want to prove that tangent theta equals the ratio of sine theta and cosine theta. Or we want to prove that tangent theta equals sine theta over cosine theta. Now we use the definition of tangent of the acute angle theta. By definition of the tangent function, the tangent of the acute angle theta, or the value of the tangent of the acute angle theta, is equal to the ratio of the side opposite the acute angle theta and the side adjacent to the acute angle theta, or tangent theta equals opposite side divided by adjacent side. Now, the side opposite the acute angle theta is x. X is the opposite side, the side opposite theta. Divide by the adjacent side. The side adjacent to theta is y. Now, we divide the numerator and the denominator by r, the hypotenuse, the side opposite the right angle. And we can do that by division property of equality. Dividing x and y by r. X we divide by r. For the numerator, divide x by r. And we also divide y by the same number r. But from the diagram, you can see that x is the side opposite theta and r is the hypotenuse. So this ratio is equal to opposite over hypotenuse, which is equal to the value of sine of theta. And the denominator y over r, y is the side adjacent to theta, and r is the hypotenuse. And the ratio of the adjacent to the hypotenuse is the value of the cosine of theta. In the last equation, we now replace x over r with sine theta, and we replace y over r with cosine theta. And we have shown that tangent theta is equal to the ratio of sine theta and cosine theta. Replace x over r with sine theta, and y over r we replace with cosine theta. So we therefore write Tangent theta equals x over r is sine theta divided by y over r is cosine theta. And this completes our proof for the first ratio relation. We have shown that tangent theta is equal to the ratio of sine theta and cosine theta. Or tangent theta is equal to sine theta over cosine theta. You do the proof of the second ratio relation. You show that cotangent theta is equal to cosine theta over sine theta. The proof is similar to the proof I just have shown you. Now we state the next set of fundamental trigonometric identities, the reciprocal relations. As I told you earlier, there are three fundamental trigonometric identities in this group known as reciprocal relations. The reciprocal of sine, written 1 over sine, is known as the cosecant of theta. This is the first of the three reciprocal relations. Cosecant theta is equal to the reciprocal of sine. And the reciprocal of sine theta is 1 over sine theta. The second reciprocal relation is the reciprocal of cosine, written 1 over cosine theta. And this is equal to or is defined as the secant of theta. And the third reciprocal relation is the reciprocal of tangent. And the reciprocal of tangent is written 1 over tangent. One over tangent theta is defined as the cotangent of theta. Cotangent of theta is equal to the reciprocal of tangent. The reciprocal of tangent is written as 1 over tangent of theta. I will prove the third reciprocal relation, and for your assignment you prove the first two reciprocal relations. To prove the third reciprocal relation, we consider again this right triangle, where the acute angle theta is placed at this vertex, and the side opposite theta is denoted by x. The side adjacent to theta is denoted by y, and the side opposite the right angle is denoted by r. And we want to prove that cotangent theta equals 1 over tangent theta. Again, we want to prove that cotangent theta is equal to the ratio of tangent theta, or 1 over tangent theta. We use the definition of cotangent of the angle, acute angle theta. By definition of cotangent function, cotangent of an acute angle theta is equal to the ratio of the side adjacent to theta and the side opposite to the acute angle theta, or cotangent theta is equal to adjacent over opposite. But from our diagram, the side adjacent to theta is y, and the side opposite the acute angle theta is x. So this equation is equivalent to the following equation. Adjacent to acute angle theta is y, adjacent is y, divide by the side opposite, the acute angle theta is x. We replace opposite with x. Now we divide both sides we divide the numerator and denominator by the same number y. We now divide the numerator y by y over, we also divide x by y, we write x over y. And y over y is equal to 1 over x over y. But x over y, x is the opposite of the acute angle theta, y is the side adjacent to theta, and the ratio of opposite over adjacent is equal to the tangent of the acute angle theta. Or tangent of acute angle theta is equal to opposite over adjacent, or tangent theta equals x over y. Cotangent theta is equal to 1 over x divided by y. But x divided by y is equal to x divided by y is equal to tangent theta. Therefore, we now write cotangent theta equals 1 over tangent theta. We have shown, therefore, that cotangent theta is equal to the ratio of tangent theta, which is 1 over tangent theta. Or cotangent theta, we have shown, is equal to 1 over tangent theta. And this shaded box indicates the end of root. We now state the last set of fundamental trigonometric identities known as the Pythagorean identities. We now state the last three fundamental trigonometric identities, and they are known as the Pythagorean identities. The first of these three Pythagorean identities says that the square of theta plus the square of cosine or square of cosine theta is equal to 1. And from this Pythagorean identity, we can derive the other two Pythagorean identities. We start with the second. Divide both sides of this equation by sine squared theta. The left hand side, sine squared theta plus cosine squared theta, we divide by sine squared theta. Equals the right hand side, we also divide by sine squared theta. And we are using the division property of equality. The division property of equality says if we divide both sides of an equation by a non-zero constant, the equality remains true. Now to divide sine squared theta plus cosine squared theta by sine squared theta, we divide each term in the numerator by sine squared theta. The first term, sine squared theta, we divide by sine squared theta. Plus the second term, cosine squared theta, we also divide by sine squared theta. And do not make a mistake of cancelling sine squared theta and sine squared theta. You cannot do that because sine squared theta is part of this sum. In the numerator, sine squared theta plus cosine squared theta. If you cancel out sine squared theta over sine squared theta, the sum would be gone. And at the right hand side, we write 1 over sine squared theta as the square of 1 over sine theta. This is by property of exponent. The square of 1 over sine theta is equal to the square of 1, which is 1, over the square of sine theta, which is sine squared theta. And now you can cancel out sine squared theta over sine squared theta is equal to 1. Plus, again we apply property of exponent. The square of cosine theta divided by the square of sine theta can be written as the square of cosine theta over sine theta. And the right hand side is the same, the square of 1 over sine theta. Now we apply a ratio relation for cosine theta over sine theta and a reciprocal relation for 1 over sine theta. The ratio of cosine theta over sine theta by ratio relation is defined as cotangent theta. And 1 over sine theta, or the reciprocal of sine theta, is equal to cosecant theta by reciprocal relation. We write 1 over sine theta is equal to cosecant theta. Hence, by ratio relation, the ratio of cosine theta and sine theta is equal to cotangent theta. By reciprocal relation, the reciprocal of sine theta, or 1 over sine theta, is equal to cosecant theta. In the last equation, we now replace cosine theta over sine theta with cotangent theta, and you have square. At the right hand side, we replace 1 over sine theta with cosecant theta, and you still have square at the right hand side. Thus, we get 1 plus cosine theta over sine theta is equal to cotangent theta by ratio relation. And you have square equals 1 over sine theta is equal to cosecant theta by reciprocal relation. And you have a square. But the square of cotangent theta is the same as cotangent squared theta. So the left hand side is equal to 1 plus square of cotangent theta is equal to square of cotangent theta equals the square of cosecant theta is equal to cosecant squared theta. And we have derived the second Pythagorean identity. 1 plus square of cotangent equals the square of cosecant. The first Pythagorean identity says the square of sine plus the square of cosine is equal to 1. The second Pythagorean identity says 1 plus the square of cotangent equals the square of cosecant. The third Pythagorean identity is also derived from the first Pythagorean identity, sine squared plus cosine squared equals 1. When we derive the second Pythagorean identity, we divide both sides of the equation by sine squared theta. For the third Pythagorean identity, we now divide both sides of the equation by cosine squared theta. We derive the third Pythagorean identity from the first Pythagorean identity by dividing both sides by cosine squared theta. Sine squared theta plus cosine squared theta, we divide by cosine squared theta. And we do the same for the right hand side. 1, we also divide by cosine squared theta to maintain the equality. At the left-hand side, we divide each term in the numerator by cosine squared theta. Do not make the mistake of cancelling out cosine squared theta and cosine squared theta. You cannot do that because cosine squared theta is part of this sum in the numerator. If you cancel out cosine squared theta with cosine squared theta in the denominator, then the sum in the numerator would be lost, would be gone. You will just simply get a single term sine squared theta, and that is not correct. So what you do, you divide each term in the numerator, sine squared theta divided by cosine squared theta, plus cosine squared theta divided by cosine squared theta. We do that, sine squared theta divided by cosine squared theta. Plus the second term, cosine squared theta, we also divide by cosine squared theta. To the right hand side, we apply property of exponent. 1 over cosine squared theta can be written as the square of 1 over cosine theta. By property of exponent, the square of 1 over cosine theta is equal to the square of 1, which is the numerator, divided by the square of cosine theta, which is the denominator, cosine squared theta. Now you can cancel out cosine squared over cosine squared because it is equal to 1. Actually, we do not cancel cosine squared over cosine squared theta. We write 1. And for the first term, we apply again property of exponent. The square of sine over the square of cosine can be written as the square of sine over cosine. Again, the first term by property of exponent, sine squared theta over cosine squared theta is equal to the square of sine over cosine, plus cosine squared theta over cosine squared theta is equal to 1. Now we apply ratio relation to the ratio of sine and cosine, and we apply reciprocal relation to the reciprocal of cosine theta, which is 1 over cosine theta. To simplify this equation, we use the ratio relation. By ratio relation, the ratio of sine and cosine, or sine over cosine, is equal to tangent theta by ratio relation. And the reciprocal of cosine, or 1 over cosine, is equal to cosecant theta by reciprocal relation. By reciprocal relation, the reciprocal of cosine theta written 1 over cosine theta is equal to secant theta by reciprocal relation. Thus, we replace sine over cosine with tangent theta, and we replace 1 over cosine theta with secant theta. Sine over cosine is tangent theta squared. Plus 1 is equal to 1 over cosine is secant theta squared. But the square of tangent theta is equal to tangent squared theta. Plus 1. And the square of secant theta is equal to secant squared theta. And this is the third and last of the three Pythagorean identities. The square of tangent plus 1 equals the square of secant. We now summarize the three Pythagorean identities. Number 1, the square of sine plus the square of cosine is equal to 1. Number 2, 1 plus the square of cotangent equals the square of cosecant. And the third, the square of tangent plus 1 is equal to the square of secant. Now I will prove the second Pythagorean identity, and for your assignment you prove the first and the third Pythagorean identities. To prove 1 plus square of cotangent equals the square of cosecant, consider again this right triangle with the acute angle theta at this vertex, and the side opposite theta equals x, and the side adjacent to theta is y, and the side opposite the right angle is r. And we start from the left hand side. From the left hand side, 1 plus cotangent squared theta, we will try to derive squared of cosecant theta. As I said, we will start from the left hand side, 1 plus the square of cotangent theta. So we write first the definition of cotangent function. By definition of cotangent function, the cotangent of an acute angle is equal to the ratio of the side adjacent to the acute angle theta and the side opposite the acute angle theta. But from our diagram, the side adjacent to the acute angle theta, this side adjacent to acute angle theta is y. Over the side opposite the acute angle theta is x. And in this equation, we replace cotangent theta with y over x. First, we write 1 plus cotangent square theta as 1 plus the square of cotangent theta. One plus the square of cotangent theta is equal to 1 plus cotangent theta squared. But cotangent theta, the value is y over x. So the right hand side is 1 plus y over x is squared. And by property of exponent, the square of y over x is equal to the square of y divided by the square of x. Hence, the right hand side is equal to 1 plus y squared over x squared. And we combine 1 plus y squared over x squared using LCD or lowest common denominator. To combine 1 and y squared over x squared, we use the lowest common denominator. If you write the denominator of 1, the denominator of 1 is 1. And from your course in algebra, the LCD or lowest common denominator of 1 and x squared is x squared. And we find the numerator of the sum by dividing the LCD by each denominator and multiplying the quotient by the numerator. X squared divided by 1 is x squared, multiplied by the numerator 1 is x squared. Plus x squared divided by x squared is 1, and 1 multiplied by the numerator y squared is equal to y squared. Now, to simplify, we apply the Pythagorean Theorem to the numerator. We will find an equivalent value to the sum of x squared and y squared by Pythagorean Theorem. From this right triangle, you can see that r is the hypotenuse, x is the opposite side, and y is the adjacent side. And the Pythagorean Theorem says that the square of the hypotenuse is equal to the sum of the squares of the two other sides. Or in symbol by Pythagorean Theorem, r squared is equal to the square of x plus the square of y. Hence, we replace the numerator x squared plus y squared with r squared. And we get 1 plus cotangent squared theta is equal to x squared plus y squared equals r squared. Divide by x squared. Now, we divide the numerator and denominator by r squared. At the left hand side, we still have 1 plus cotangent squared theta. R squared, we divide by r squared. And x squared, we also divide by r squared. At the left hand side, we have 1 plus cotangent squared theta. At the right hand side, numerator r squared over r squared is 1. 1 divide by. In the denominator x squared over r squared, we apply property of exponent. We write the square of x over the square of r as the square of x over r. The square of x over r is equal to the square of x divided by the square of r by property of exponent. But x is the side opposite the angle theta, and r is the hypotenuse. And x over r is equal to the sine of theta. Or sine of theta is equal to opposite x divided by the hypotenuse r. Thus, x over r is sine of theta. Again, we know that by definition of sine function, the sine of theta is equal to the ratio of the opposite side, x, divided by the hypotenuse, r. So this ratio x over r is equal to sine theta. Hence, we have 1 plus cotangent squared theta is equal to 1 over x over r is replaced with sine theta squared. And this 1 over the square of sine theta by property of exponent can be written as the square of 1 over sine theta. Again, the square of 1 over sine theta by property of exponent is equal to the square of 1, 1, divided by the square of sine theta square. But the reciprocal of sine, which is 1 over sine theta, by reciprocal relation is equal to cosecant theta. We now replace 1 over sine theta with cosecant theta. The reciprocal of sine theta, 1 over sine theta, is equal to cosecant theta by reciprocal relation. Hence, 1 plus cotangent theta cotangent squared theta is now equal to 1 over sine theta is cosecant theta squared. From this last equation was 1 plus cotangent squared theta is equal to 1 over sine theta is replaced with cosecant theta by reciprocal relation to the power 2. And the square of cosecant theta is equal to cosecant squared theta. Therefore, we have shown that 1 plus the square of cotangent is equal to the square of cosecant, or 1 plus cotangent squared theta is equal to cosecant squared theta. And that completes our lesson for today. In the next lesson, we will apply these 8 fundamental trigonometric identities in finding the values of other trigonometric functions of unknown angle, but the value of one of its trigonometric functions is given. And also we will apply these fundamental trigonometric identities in proving other trigonometric identities. And don't forget to do your assignment. You have 5 numbers to prove the other fundamental identities. You have 2 Pythagorean identities to prove, 2 reciprocal relations to prove, and 1 ratio relation to prove. And don't forget to subscribe to my YouTube channel, Art Kalisan, the channel of learning and leisure. And also ask your friends or classmates to subscribe to my YouTube channel so they may learn as well. Thank you for joining me in my class today.